Let's look at number 23, which is one of the trickier ones from the last homework. It's that we have this, I don't know why they call it A, they call it anything they want, but it's x times x plus 3, and we want to graph this thing using calculus, right? How can we make a nice easy graph of this, showing all the important things just using calculus? Okay, so first we can see that x can't be less than -3, or we get the square root of a negative number. We're not going to go there. So that's nice. We only have to start our graph at -3, and then x can be anything bigger than that. Okay, so typically the first thing we want to do is figure out what the slope of this thing is. How is it sloping? Is it positive, negative? Where does it switch over? So we take the derivative. So a prime of x, we're going to have to use the product rule. The derivative of x is 1 times the second thing times the square root of x plus 3 plus the first times the derivative of the second. Derivative of that is 1/2 x plus 3 to the -1/2 times the derivative of what's inside. Derivative of x is 1, derivative of 3 is 0, so just times 1. Okay, that's our derivative. Let's rewrite it so it makes more sense, looks more like something we can deal with. So our derivative is, don't have to write the 1, square root of x plus 3 plus, let's see, the x is on top, and the 2 is in the bottom, and this is in the bottom because it's negative, and that's just a 1, so 2 square roots of x plus 3. Okay, that tells us our slope. So one thing we can do is look at it and say, okay, this is always positive, square roots can't be negative, the bottom here is always positive, so this can only be negative where x is negative. So at some point maybe it would be negative when the negative here outweighs negative x will make this whole side negative. So when does this become bigger than that? That's where you could have a negative slope. But for the most part, we're going to have a positive slope. So where it switches over is when the slope is 0. On one side, if its slope is 0, it's going to be always positive, and at 0 it's going to switch over, and then maybe it's negative on the other side, or maybe it's not. Maybe it'll never be negative, so we got to figure that out. So first thing I'm going to do is figure out where it's 0. That's always an interesting point. Oh, and the other thing is, at x equals -3, which is our extreme point anyway, we have a dividing by 0. So at x equals -3, the slope a prime is infinite, which is undefined, which makes that interesting. When we graph it, we want to have like a straight up and down slope right there, because we know it's infinite, which is again called a critical number because it's interesting. That's a good point to know about. Okay, so we know -3, but have a perfectly steep, straight up and down slope. Okay, so set that equal to 0. Let's put the x plus, let's put this on the other side, doesn't matter. Square root of x plus 3 equals -x over 2 square root of x plus 3. C, multiply both sides by 2 square root of x plus 3. Get rid of the denominator, so times 2 square root of x plus 3. This works out really nice. The x plus 3 square roots cancel. So I have 2 times x plus 3 equals, over here I just have -x left, equals -x, or 2x plus 6 equals -x. Let's put the -x over here, make it positive. Put the 6 over there, make it negative. So we have 3x equals -6. Divide both sides by 3. X equals -2. So at -2, we have a slope equals 0. So I'm just going to write that to remind us. That's our critical number was only 1. So we have 2 critical numbers here. Slope is 0 at 1 point, -2. Sometimes there's 2 or 3. There's only 1 here. And where it's infinite. So already we know something about our graph. We know where those points where it's infinite slope and where it's 0 slope. Okay, but 0 slope means it could be like this, it could be a minimum, or it could be a maximum, or it could be something in between, something like this, which is an inflection point. So we got to figure that out. Now one way we can do it is we can plug in numbers on either side of -2. So -2 is the bottom here, so if it's, or the top. So if it's negative on one side and positive slope on the other side, we know it's a minimum. If it's the other opposite, positive on one side on the left, decreasing on the, or negative on the right, we know it's a maximum. Or if it's the same on both sides, we know it's one of these. So we can take like, what, negative 2.1. So that would be somewhere over here, like negative 2.1, negative 1.9. We can plug that back into our formula for the derivative. So plug in negative 2.1, negative 1.9, all this kind of stuff, and get an answer, see if it's positive or negative on either side. Or we can take the second derivative and see what the second derivative is at negative 2. If the second derivative, if a double prime is greater than 0, a double prime at negative 2, we take the second derivative, plug in negative 2, negative 2. If it's greater than 0, then it's a minimum, which always seems kind of weird. Things like, oh, it's big, it's a max, but that means, because that means that it's going from negative, the derivative is changing from negative to positive, and the second derivative tells us how the derivative is changing. If the second derivative is positive, greater than 0, it's changing from negative to positive. And if the second derivative at negative 2 is less than 0, obviously it's a minimum. And if the second derivative at the point negative 2 equals 0, then we don't quite know what's happening, but it certainly could be an inflection point, because many times inflection points are where the derivative is 0 because it switches over. Inflection points where it switches over from concave up to concave down, and that's where the second derivative is 0. Because if there's a maximum and a minimum, right, at some point it switches over from up to down, and that's the inflection point. And if this is where the second derivative is greater than 0 to less than 0, it's got to be 0 somewhere in between. Okay, so we have two options. We can take the first derivative, plug in negative 1.9, negative 2.1 into our formula to get if it's increasing or decreasing either side, which is what we want to know anyway. Or we can take the second derivative, which we'll probably want to do anyway. So let's just take the second derivative. So let me rewrite our derivative. A prime of x is equal to square root of x plus 3 plus x over 2 square root of x plus 3. Now we got to take the derivative of that. Looks like it's going to be some work. So take a deep breath. This part's easy. That's 1/2 x plus 3 to the negative 1/2. And we're done, times the derivative of what's inside, which is just 1. Okay, we're done with that. Here we're going to have to use the quotient rule, which is good practice. Derivative of the top times the bottom. Derivative of the top is just 1. So it's times the bottom, which is 2 square roots of x plus 3, plus the top times the derivative of the bottom. Well, the 2 just stays there. And then this is just the derivative of x plus 3, square root of x plus 3, so we know that. So that's 1/2 square root of x plus 3 to the negative 1/2. So I shouldn't write square root of x plus 3. It's 1/2. Derivative of the bottom is 2 times 1/2 x plus 3 to the negative 1/2. X plus 3 to the negative 1/2. Divided by the bottom squared, which is 2 squared is 4. X plus 3 squared is just x plus 3. Okay. We want to know what this is when x equals negative 2. And if it's greater than 0 or less than 0, it'll tell us some interesting things. This is a mess. But we can figure this out pretty easily. Just plugging that in. And good thing is negative 2 and 3 just make 1. So this is not as bad as it looks, because every time you have the square root of x plus 3, we plug in negative 2 there. So what is it at negative 2? The square roots go away because they just become the square roots of 1. So at negative 2, this is just square root of 1. Doesn't matter if it's negative, 1 on the bottom. It's just 1 to any power is 1, because negative 2 plus 3 is 1. Yep, that's right. So that's just 1/2 plus 2. This is, again, anytime you have the square root of x plus 3 is just 1. So that's just 1. Here we have the 2 and the 1/2 cancel. So that goes away. So here we have x, and x is negative 2. So it's negative 2. And this again is 1. Divided by x is x plus 3 is this 1 divided by 4. But look, 2 plus negative 2 is 0. So it's just equal to 1/2. So it looks like it's going to be a lot of work, but it's not. So the derivative, second derivative of negative 2 is positive. That means that, like we talked about up here, that means that it's got to be a minimum. Where if the second derivative is positive, it's a minimum at negative 2. Now if it's a minimum, that means that the slope, we know the slope is positive on this side. That means it must be negative on that side. And it only goes to x equals negative 3. And for it to be, again, a minimum has to be negative here. And if it's, because again, right, because it's got to be positive here, negative here. And since it never gets to 0 again, it can't switch over. So we know for sure that from negative 3, so I'm going to say, write it this way, from negative 3 to negative 2, on this side, the slope, it's got to be, yeah, I'll just say, so the slope A prime is less than 0, so that means it's decreasing. And everywhere else, the slope is positive because it never switches over again. So from negative 2 to infinity, we know that the slope is greater than 0. It's increasing. And that's because we know it's got to be positive here, and there's no inflection points. There's no place where the second derivative is equal to 0. And so it's going to be, yeah, it's going to be all the way there. It's got to be increasing for the rest of its life. Okay, that's kind of cool. Now, how about concave up and concave down? It switches over at an inflection point, but we know that, let's see, at negative 2, there's only one place where the slope is 0. And that's it, it's negative 2, and we know it's a minimum. And there's no places where the second derivative is, actually, yeah, we don't know that. Is the second derivative equal to 0 somewhere else? The second derivative equal to 0. That could be another inflection point. So we didn't figure that out, but if we look at this, let's see. No, there can't be, because this is always positive. So you can see this here. Sorry, this is our second derivative. This is always positive, and this is always positive for positive x. So there is, excuse me. So there is no place where the second derivative can be equal to 0. There are no like inflection point kind of places where it switches over from concave up to concave down. And the only weird place is x equals negative 3. So basically we can graph this now. So I'm going to make my graph down here. We know that at negative 3 the slope is infinite. So let's figure out what is the point at negative 3. So we got to go back here. So at negative 3 it's 0. So negative 3 and 0 is a point. And we know the slope is infinite there. Now we know at negative 2, that's where the slope is 0. So we go back here at negative 2, this is 1 inside, and that's negative 2. X is negative 2, and here is negative 2 plus here is 1. So it's just negative 2. So if this is 3 here, this is negative 3. Negative 2 would be maybe right here. So at negative 2, x equals negative 2 and y equals negative 2, so something like that. That's where the slope is 0. We know it's negative, and then we know it's positive. And and we know the slope is infinite right there. So I drew that wrong. It's got to be going straight down right there, and then it curves to 0, because at negative 3 it's infinite slope. So straight down, and then curves to 0, and then it goes positive. And let's do one more point. When x equals 0, we can't have x equals, yeah, when x equals 0, we get 0. So when x equals 0, y is 0, so we can put a point there, and then it goes like this, and then it just goes up and up and up, and we know it doesn't switch over anymore. And so since the second derivative is greater than 0 for all these places, we know this is concave up. If the second derivative is ever equal to 0, we know, oh, maybe it switches over or something. But it can't, because there's no other 0 slopes. So if it switched over to concave down, there'd be another 0 somewhere. So it doesn't. So really, we're pretty much done. we can safely say that we figured out all the interesting points, and this is what the graph looks like. And if you check on Desmos, you'll see it looks like this. So, okay, and then again, it's concave up everywhere. So you'd say from -3 to infinity, it'd be concave up. There's no places where it's concave down. These problems take a lot of time. They're a lot of work. You pretty much take like a full page per problem if you do it right. So I didn't give a whole lot of them to do, but they're really good practice with taking derivatives and seeing what those mean. So, okay, thanks for watching.